Atish is doing his PhD at IIIT Delhi, and he's been a research associate PDoc with us for last 1 year.
Good evening, everyone. So basically, I'll be talking about a project which we are doing at the center, which is basically where we are trying to estimate the potential economic damage from climate change in India. Is it better? Okay. Yeah. So we are trying to estimate the potential economic damage from climate change in India. I'll be talking about a specific part of this project, which involves coming up with granular projections of climate variable for India. So basically, developing countries are with low adaptive capacities when it comes to climate change and are obviously vulnerable. So any mitigation strategy would require you to get precise estimates about the future. For that, CMIP6 models serve as the benchmark and the gold standard, where and are also used for in the IPCC reports. What these models do is they provide you, according to emission scenarios, projections of various climate variables, and we intend to use them. However, using all the CMIP6 models without careful analysis can be problematic because these models do not seem to work for every region. And specifically for India, a lot of them do not mimic the Indian climatology well. So one of the papers that came out in Nature Scientific Reports last year was by Rahman and Peckett. So they ranked CMIP6 models for two climate variables, which is minimum and maximum temperature. And they came to this conclusion that there is an ensemble of 5 to 6 models which do a better job of predicting matching India's minimum and maximum temperature trends. So this figure that you see here is basically shows the correlation and the standard deviation. So very few models have correlations of, let's say, zero point 0.8. A lot of them hover around 0.6. Some of them are even lower. So the idea is we will be using 5 to 6 models to come up with very precise, oh, I thought there was a message, very precise granular estimates for climate variables. So just to show you what CMIP6 projections look like, so these are the four graphs which represent four scenarios from lowest emission scenario to highest emission scenarios. So, and this is for maximum temperature. One peculiar thing that you would notice is that except for the lowest emission scenarios, which is SSP 2.6, where the forecast seems to be very volatile. Okay, so sir, this is basically four scenarios. So first graph is lowest emission scenario, which is SSP 2.6. The next graph is SSP 4.5. The third one is SSP 7.0. And last one is SSP 8.5. In the increasing order of emission, so 2.6 is lowest emission, 8.5 is highest emission. So these basically lines in each of the graphs shows what predictions these selected CMIP6 models are making. So no, there's no ground truth. So x-axis is 2030 to 2070. Yeah, it's all future. So it shows how the maximum temperature will look like according to these models. You can see a clear trend for three scenarios. For the lowest emission scenario, you see a very volatile trend, so which will get reflected in our projections as well. Here we have the minimum temperature for the selected ensemble of 5 to 6 models. And again, for low emission scenarios, you see a lower change in temperature, and for highest emission scenarios, you see a higher trend, which is obvious. Yeah, yeah. Yeah, yeah. Yeah, but I mean, for historical simulations, this one particular model was considered in the, it matched the historical simulations well. Uh, uh, so this is the CAN ESM 5. In fact, this is included in both minimum and maximum temperature, according to the paper. Yes, yes, they do. Yeah, that's absolutely true. But this is the recommended model. I mean, we can obviously tweak with the model selection and probably come up with our own rankings as well. But this is the recommended ensemble. Yeah. Okay. Okay. I've I've added a line like that in the results later, but yeah. So the data that we have is basically ERA 5 reanalysis data for minimum and maximum temperature at 0.25 grid level. And the period that we have selected is 1960 to 2014. Sorry for the typo. So the idea is basically we have an ensemble of 5 to 6 models. We have the ground truth. We want to come up with some sort of an optimal weighting criteria for each of these models so that we can predict in the future how the future would look like. So, and for that reason, we have trained a model where ERA 5 ground truth data acts as the target variable and the CMAP 6 model data acts as the features. So we have done this exercise for minimum and maximum temperature at 0.25 resolution. So uh, the model has been trained on 1960 to 2003 and validated on 2004 to 2014. So the model architecture that we have chosen is is known as spreadformer. It's a transformer-based architecture. It makes a minor change in the transformer architecture by replacing the feed-forward neural networks with gated linear units, which helps with computational efficiency. Uh, yeah. So these are some of the results. So if you look at let's we have taken a random sample from the validation, which is yeah yeah yes sir. 0.25 so 1 day. It's a daily data. Yeah. It's a, yes.
I have a question. You are saying that CMIP 6 data is at 0.25 degree. Is it downscale data or
Yeah,
bias
it's
correct?
the downscale data. Yes.
Is it next GDDP or CMIP data?
So sorry, I could not hear.
Which data set is it?
So,
The CMIP 6 data? Which data set you are using here?
yes, it's NASA next.
Next GDDP.
Yes, yes.
Okay. Yeah. Yeah. Okay. Great. Thank you.
Yeah.
Hello?
Yeah.
Are free run simulations.
Okay.
Okay, so 1960 doesn't mean real 1960. Okay, so these are the free run simulations.
Hmm.
And treating them as real 1960 data. That is the
Okay.
you need to limit.
Yeah.
I mean, he could probably try to bias correct the mean structure, the variance, standard deviation, all those stuffs, the mean state. But one-to-one comparison on daily basis is not the right way of doing. Parthoda, am I right? I mean,
So what he is telling,
Hmm.
Professor Ravi, he also mentioned
Hmm.
so climate model which are coupled to ocean,
Hmm.
which are used for projection.
Yeah.
Okay, so they don't care for uh, any particular year.
Okay.
Okay, so let's say it may start from 1850 or something. Okay, and so at the starting point,
Hmm.
they prescribe the sea surface temperature, some level of carbon dioxide, blah blah blah. Okay, then just they let it run. Okay,
Okay.
so it will run.
Hmm.
Meanwhile, again there'll be double the carbon dioxide, the SSP scenarios, etc. That will be separate experiment. But then what they do when the model started, so they allow, I think, almost 10 years or maybe 20 years because
Oh,
couple model,
yeah, it's
all
been
that system, this thing to stabilize.
Hmm.
Then they feel that, okay, now the model has come to the current stage. Okay. So after 20, removing 20 year, first 20 year, whatever you get from that date, from that, time, you take another, say, 50 years and consider that this is the historical natural, that is the current time. Okay, and then you consider another 100 years. Okay,
Hmm.
so now you compute from 1860, so it would be broadly, you can say 1860 to say let's say 2015 or something, and then another 100 years to
but
2100.
but year doesn't have a real meaning in
Yeah,
that.
it will not have any real meaning.
I mean, this is random. I mean,
It is
doesn't
random. Yes,
doesn't
correct.
make much sense. Yeah.
Yeah, it is dummy.
So actually,
Yes.
the real comparison, if you want to do, you need to use a hindcast. That is the only possibility. I mean, these are free run simulations. And even in the hindcast, if you let the model start, let's say on 1st Jan and let it run for a year,
Hmm.
you cannot do a year to year, I mean, day-to-day comparisons because of
No,
the chaotic.
what they can do is
The,
that the projection can be downscaled.
That no, I'm saying the way they are doing, they are trying to match on daily scale
No, that is
the
true. Yeah.
model and analysis. That is not probably correct. But ground truth, you mean still on daily scale, ground truth and daily scale model comparison is not the right way to do.
Yeah, I'm doing it
Yeah,
differently.
so the probably what he can do is he can try to just correct the statistics of all these years of simulations, but not one to one match.
So correct the statistics. Okay.
Yearly
Here,
also doesn't make much sense actually, because 1916 SIMIP it may not be the representative of 1916 actual. So that is the point, because these are the free run simulations.
true.
That's what I'm saying. If you want to just bias correct the historical runs, you could bias correct the entire mean period, their variance. uh, There may be there may be the PDF approach you can probably take
Yes.
will be a much better approach. Let's say temperature distribution from your CIMIF, you have some distribution of temperature, and from ERA you have. Now you try to just match the PDFs instead of going on daily time scale and trying to match them.
Yes,
That
correct.
would be a better way.
So
Probability density function.
so in
I mean, that signifies the overall statistics of the distribution of temperature that is trying, the model is trying to simulate. But you forget, you don't have a memory of the dates and time. It is just the
So,
PDF of
so
temperature
every
that.
grid you try to see the PDFs of temperature or precipitation or even some other parameters, that you can.
Maybe what you can do is you can just try to minimize the KL divergence between. uh,
No, we can take an average, no, whole India average.
and that's what I'm saying. At each grid point, maybe once you have matched the PDF, now you know that these models. Once you match the PDF, now you can reproject on the temporal scale.
Correcting the bias.
Correct after correcting the bias.
Oh,
Yes.
Uh,
Yeah.
Sir, I have a point here. Sir, these data sets are bias corrected with the reanalysis data set of GMFT by taking a consideration of cumulative distributive functions of 30 days means. So I think, sir, it's even we validated these data sets, it's performing very good, sir. Then comparing to actual model data sets. So I mean, even I had tested for the 20, actually the model simulation, historical simulation ends at 2014.
Yeah.
Especially next DDDP.
Can you please just repeat your question? It's not clear.
Uh, it's not a question, sir. It's a clarification. So next DDDP data set is a very good model over India. It is performing better than the original SIMIP data. And these data sets are bias corrected using GMFTL reanalysis data set by using the cumulative distributive functions of 30 days means. So these data sets are very good, sir. It's performing very well.
He's suggesting a data set. I'm not sure.
No, I'm not suggesting, I'm giving the clarification. These next
Alright.
DDDP data sets are very good.
Okay. But let me ask you this. Now, Atish, this Nature paper where you saw these models were good for India,
Yeah.
do they talk about time periods being faulty and not being useful, or?
No, they do not talk about this. And in fact, so
Code.
yeah.
Actually, they are, you were showing the Taylor's plot. Okay, so what they essentially do that they give three numbers. One is correlation. That is correlation is in space, not in time. And standard deviation and RMSE. The first plot that you showed, Taylor plot.
Yeah.
And you want the model to fall at the lower, I mean lowest circle, the smaller circle, and at one ideally.
Yeah.
And the departure from that model gives you an idea at how bad the model is.
Yeah.
So probably I can think of like the matching the PDF would be a better way. You can just minimize. Let's say the PDF is truth and a conditional PDF of the model given this, or maybe a KL divergence kind of thing you can minimize. That is based upon the mean.
They do temporal.
Temporal what?
So
Temporal correlations they cannot take. They will take temporal mean, temporal standard deviation, and compare with the observation.
They have done it at grid
But
level.
one-to-one comparison year by year they cannot do. That is not the.
So they have done it at grid level. Yeah.
What he is telling, you cannot show interannual variation, interannual
So 90
analysis
Okay.
from semi model run and observed time series.
Okay.
Let's say just for example, I'm giving you. You take any CME model out of this from 1960 up to 2014. Take average over Central India or all India, and just raw data. You just try to see the time series of era 5 and this one. You will get zero correlation, that I can assure you, because that is not the representative of the actual time series. That is the point.
All right. So regardless, I'll yeah, yeah, yeah. So this is yeah. So we trained a model using those ensemble of five models, and basically the era 5 reanalysis data was the target. So we have picked this random date from 2011, which is 1st of May. So what you see here, leftmost graph is the ground truth. And these four graphs I've chosen from the ensemble of those models. We have the error. So more green patches show higher error, and which is obviously bad. And once, so after, yeah, yeah. So, so yeah, the mean. s- Yeah, all right.
No, they
With-
see for CMIP they can do a statistical approach, but there are some R system model hindcast available nowadays. Yes, so you can actually, nothing to this about.
Nee,
You
nee.
can take this R system model hindcast
Okay.
and just follow what you are doing.
So replacing Era 5 with the.
No.
Okay.
Era 5 is your target.
Okay.
Keep that.
Okay.
CMIP.
Oh, CMIP I should.
CMIP you
I should.
replace by ESM hindcast.
Okay.
Some by using these models. So
Yeah.
that is might not be possible.
No.
Do they model
No,
also have
they
projection?
forecast as well.
They have projections
MPI,
also.
ESM, yes.
So then you can use those models.
That I
Will
will
give a
find out and let you know.
Okay.
that will be a better representative of what you are trying to do.
Yeah. Y- Um, yeah. So I mean, this is fairly. So the sequence length can be improved. I mean, there are a lot of things that we can do to probably improve this. But if you see that the green patches are substantially lower in this case as compared to here, so where you have more green patches. So error is more than 3 in each case. Mean absolute error. Yeah, between 3 to 4 degrees. Here it comes down to 1.6. And also this graph for the entire month of May, where on the left you see that the um, MAE of these graphs, MAE of these models was between 2.7 to 4.5, and our model, the error was around 0.79 to 2.5. So even for the entire month, the error came down. So yeah, so this is basically the projection for annual maximum temperature for the most extreme and low emission scenario versus high emission scenario. So these are the trends that we see at the annual level, the temperature rise. And this is for the month of May, maximum temperature on average. So you see that the volatility of those CMIP 6 models is getting reflected in the low emission scenario, and a clear trend, clear rising trend in the high emission scenario. So yeah, so this is the average maximum temperature for May 2070. So yeah, you see darker map in the high emission scenario slightly. Yeah. So we have done this exercise for minimum temperature as well, where we took the ensemble of models and we tried to do the same thing. We trained the same model. And then here also we see lower error. Yeah. So yeah. Yeah. Okay. I so so one of the things that we eventually want to do is that we want to capture trends like hotter summers, colder winters.
Yeah, exactly. So annual characteristics. These are
Okay.
annual
Okay.
characteristics,
Okay.
right? So what you could do is you could look at these. Uh, so the historical runs, which sort of was saying these are free runs, but you could think of them as like if you aggregate the statistics for a year. So what is the probability distribution of temperature given not the year 1960, but given the forcing value, carbon dioxide
Okay.
ppm 370 ppm or something like
Okay.
this. You know, so it's a conditional distribution based on the carbon dioxide, right?
Yeah.
And then 1970 might have a different conditional distribution. And then you train a model which knows how to sort of mix the information between the models based on what is the current condition, what is it conditioned on, what carbon dioxide concentration is it being conditioned on.
All right.
And then in the future, when it will encounter other values of carbon dioxide, it probably will know, what should I do in these kind of situations. Carbon emission is just actually one of them. I mean, there's a whole bunch of anthropogenic. In fact, like the best way would be like these SSP scenarios. Like they would have a kind of they would have a forcing curve, and that forcing curve, maybe that value should be taken. Yeah. Yeah. Exactly. Exactly, something along those lines.
I think that makes sense. Actually.
And to course grain the whole analysis, to move away from the daily scale.
They can still do daily scale. There is no problem. Only thing they should not compare that daily scale with the
Another daily
The
scale.
daily
Yeah.
scale, yeah.
daily scale analysis still.
Daily
Yeah.
scale, even let's say you are saying 1st December 2011, if you just say 1st December, that should also be fine. But 1st December, all the years mean you can compare with all the years mean from your
But here,
reanalysis.
here what is happening is so
I mean, I think I, maybe there is some confusion about how to interpret CMIP data. That's why, I mean, because he might not be from the field, so he might be taking these dates as exact dates. So that is only confusion.
So I once also because I had a similar student who was doing something quite similar, and then I got the criticism from a climate modeler who basically told me this, that look, also in the historical period, um, you can talk about maybe yearly stuff or maybe decadal stuff, because the climate models themselves, he had this objection that like climate models are more or less a stochastic process at the daily level, because when they are designing the climate model, when they are tuning all the parameterizations and calibrating the climate model, they are not looking at daily characteristics at all. They look at 30-year averages. So when you're developing a model and you now have the, let's say, temperature field from the model, right? Yeah. Ground truth, yes, they do match them to the ground truth, like the ERA5 or whatever reanalysis you have, NCEP, NCAR or something like that, but 30-year averages. So nobody's controlling these models at the daily scale. So in that sense, the daily scale, you cannot rely. So the idea is that you cannot rely on what's going on the daily scale, because nobody controlled that. Nobody went to that granularity. That may be, that may be. Yeah, and the risk is like today so we must talk that we might be over like you stand the risk of overcorrecting, like I mean, the problem is not ill posed. The problem is well phrased, and like it seems like there is a way out. I mean, this not for you should not be disheartened. I mean, this.
Yeah.
Yeah.
So we've recently started this thing. So I mean, the idea was we to use CMIP6 models in the same way that was used in some other economic studies as well. So they had used CMIP6 models to capture, let's say, in a particular season, how many hotter days, colder days. So let's say even if the number of warmer days go by, let's say 15 days, then it would have an impact on yield. Same thing during winters. So it was, I think, in that spirit. But yeah, we can probably take a feedback.